Find maximum separable line. In the graph, you can see the line succeeding is separating the two classes, and in the meantime reducing the dimensionality of our problem from two features, x1, x2, to only a scalar value y. We need to define a measure of separation between the projections in order to find a good projection vector. The mean vector of each class in x and y feature space is lambda and lambda respectively. We then can choose the distance between the projected means as our objective function. However, the distance between the projected means is not a very good measure since it does not take into account the standard deviation within the classes. The solution proposed by Fisher is to maximize a function that represents the difference between the means, normalized by a measure of the within-class variability, or the so-called scatter. For each class, we define the scatter, an equivalent of the variance as sum of square differences between the projected samples and their class mean. S, 2 over I, measures the variability within class Wi after projecting it on the y space. Thus, S 2 over 1 plus S 2 over 2 measures the variability within the two classes at hand after projection. Hence, it is called within-class scatter of the projected samples. The Fisher linear discriminant is defined as the linear function Wtx that maximizes the criterion function, that is, the distance between the projected means normalized by the within-class scatter of the projected samples. We need to express Jw as an explicit function of W in order to find the optimum projection W. In multivariate feature space X, we will define a measure of the scatter that are denoted as scatter matrices. In the given equation, SI is the covariance matrix of class Wi. SW is called the within-class scatter matrix. Now, in feature space X, the scatter of the projection Y can be expressed as a function of the scatter matrix. Similarly, the difference between the projected means in Y space can be expressed in terms of the means in the original feature space X dash space. We can finally express the Fisher criterion in terms of SW and SB as given in the equation. Find the maxima of JW by differentiating and equating to 0. Solving the above differentiation yields optimal direction for projection. Hence, J of W is a measure of the difference between class means normalized by a measure of the within-class scatter matrix. Demo labeled feature reduction. Problem scenario. Consider the IRIS dataset preloaded within the MLX10 library. Segregate the data and labels accordingly, and transform the data to two linear discriminants. You are supposed to perform LDA as a dimensionality reduction technique. Let's import the inbuilt data set. Import the required libraries. Import linear discriminant analysis from MLXtend.featureSelection. We will set a dataset now to the loaded data and define X and Y as the training and target variables respectively. Also standardize the X variable such that it is aligned on the same scale with the output. It is better to have the input value centered around 0. Initialize the linear discriminant model with the number of discriminants set to 2. We will now fit and transform the model on our data. Now that we have transformed our data using LDA, let's quickly recap the steps we have covered. Import libraries and the data set. define the data and target values, initiate LDA, transform the X variable using LDA. This brings us to the end of feature engineering. You will now be able to demonstrate feature engineering and its significance using Python, practice different feature selection techniques,